Alrighty, so last time we were talking about integrals, and this time we're going to talk a bit about probability. And we'll start off with something called the complex conjugate. I'm going to actually calculate in probability using complex conjugate. Then we'll probably finish off with some operators like momentum, position, just to be easy. And this will all be relevant at another time too, so might be a good idea to pay attention. So, complex conjugate. What does that mean? Well, we better start off first with complex numbers. Sorry about that. Let's imagine that we have an expression 4 plus 7i. This bit, yes, there's imaginary numbers here. This bit is what we call the real number. And this bit is what we call the imaginary number. And together, this whole thing is the complex number. Complex. There are lots of examples of complex numbers. But complex conjugate is pretty simple. Let's say, so you see, complex conjugate. So let's say that this expression is equal to, sorry that, I call this a y. But y star, which we call this is the complex conjugate. This will be equal to 4 minus 7i. Another example, we could have an equation psi is equal to, let's say, sine of x plus I times, let's go with something different, I x. Then psi star is equal to sine of x minus I times x. Now, why is this relevant? Well, we have to, some of the time, our wave function will feature imaginary numbers. So, you can imagine, how should I say this? Suppose that we have an equation. This has to do with how we calculate probability density. If we have a wave function, let's make it something better. Sine of x is equal to psi. Well, then this is 0. It's going to look a little bit like this. And the way that we calculate probability is using integrals. Say, from x1, whatever that might be, to x2. But you might notice something important. There's the same amount of volume here as under here. So if we integrate from this spot to this spot, this whole thing would be equal to 0. And that doesn't make any sense. We can't have 0. So one thought you might have would be to take psi squared. This will cause the whole function to become positive. So instead of having something like, something that goes up and down, it's going to be a little bit like this. Doesn't quite touch the bit everywhere, but as you can see, all of it is above our x-axis, which means the integral will not be 0 anymore. It's going to be a positive number, and it's going to be remember what I said about it being imaginary. Let's say that, for example, psi is equal to, I better highlight this, I times of sine x. Or furthermore, let's say that's something like, I don't know, sine of x plus I. Well, hang on, oops, I had an error. Ignore that. Point is that if this is, I, then this integral would actually be imaginary. And that's not good. We don't want an imaginary probability. So, in order to make the imaginaries go away, we have to take the complex conjugate. So, instead of doing that, we will have psi complex conjugate, which is psi star, times psi dx. And this might look a little weird, but this whole thing will actually give us the probability. So if you might recall something like, let's say, I don't know if you might remember this or not, but we had something like a box equation, something like this, where, the wave went like that, and then this, and then that. In order to find the probability of finding it in here, or say inside the barrier, or beyond the barrier out here, we have to apply this formula. And because it's an integral, the higher the wave function, the more likely the probability. And because complex conjugate times itself, the imaginary numbers will go away. And if you need a little bit of help, I'll give an example. So let's say that psi, for some reason, is equal to x plus 2i. If we just take the integral of psi squared, well, we have to figure out what psi squared is. And this would be, x plus 2i times x plus 2i. And if you know how to factor or multiply, this would be x squared plus 2ix plus 2ix minus 4. Because I squared, this would be plus 4 times I squared. By squared is equal to -1. And so this whole shebang would just become negative. And as you can see, we have these imaginary numbers, and that's not very nice, because this whole thing will simplify to, x squared plus 4ix plus, minus 4. And this also has the added issue where if x is, say, let's say, for example, that this bit is less than 4. Well, this means this output will actually be a negative number, which means we have negative probability, and that's not very helpful. It doesn't make much sense to have a negative probability of finding the particle. That doesn't make sense. So, this whole thing doesn't work. Instead, we'll now consider psi times star times psi. What this would look like would be x minus 2i times x plus 2i. Now, if we multiply this in, this would be x squared minus 2ix plus 2ix, and then minus 4 times I squared. But But obviously I squared is -1, so this bit goes away, and our -4 becomes +4. Now you might notice some things. For example, -2ix plus 2ix, these cancel. And so we can erase these. And now it's just x squared plus 4. And this has a benefit of 1. No imaginary numbers are present. Hang on, I'm going to move this all closer so it looks pretty. There we go. Anyway, there's no imaginary numbers, but also if x is if x squared is less than 4, we don't have negative probability, so there's no chance of having a negative probability of finding the particle this way. And to finish all this up, what we would do is just integrate x squared plus 4dx, and we pick from whatever x variables we're using, x1, x2, whatever they might be. That it can be anything. That's all there is to that. Now, what we will consider are what we call in quantum mechanics operators. And what do these do? Well, they help us find the most likely situation. Because as you can remember, taking this just gives us probability, but it doesn't tell us what's the most likely value. So in order to do this, we use operators. So I should put this. The space operator is equal to just x. And the momentum, this is what we'll focus on right now, is equal to negative I. Let me check this. I've checked my notes. Yes, it's negative. Yeah, I just had to make sure real quick, because sometimes I forget. Negative I times h bar times the derivative. And if you don't know why this is here, I'll show you in a minute on how to use this. But basically, if we take this and plug it into here, in our probability expression, it will return the likely value of x. It's like the most probable idea of what x could be. Now I will show you how to, hang on, might be a good idea to not erase this. So let me just move this over real quick. I'm gonna take this, I'm gonna stick it up here. Go on of those. They will help us. So, it's a very simple fix. We take our integral and our complex conjugate from before and our function, and then we just take whatever operator we want from up here and we stick it in the middle. So if it's the space operator, it looks like this, space dx. And that's it. That's all there is to calculate this. Size equal to like x squared minus I or whatever. You probably don't need me do this for you. It's just that, you just take this and put it in. And, in the case of the momentum operator, which we're using for wave mechanics, this is going to be negative I h bar times the derivative. And you might be wondering, why does it look so funky? First of all, the derivative is there because momentum uses derivatives. Like you think of v equals momentum in classical physics. This is the analog for wave mechanics. It's the momentum of the wave. the other reason why it has like an imaginary number, imagine if we have something like e, this is very popular, negative ix. If we take its derivative, it becomes negative I e to the ix. Oh, that's negative. And as you can see, this I and this I will cancel, and so the negatives, and it all works out, you know. But we're not going to worry about that too much. It's basically just here to exist. Um, so let's say that we have, you know, let's say that we have an equation where psi is equal to, let's say, sine of x plus 2i for some reason. And we want to know what is the most likely value of x. I'm gonna move this out of the way. It's very nice to have these tools here to move things. So that's what we're trying to do, you know, trying to find this value. Well, we know that psi star is equal to sine x minus 2i. And we also know that the x operator is just equal to x. And so the way we'd solve this is we take the integral from our limits, whatever it might be. It doesn't really matter. We're just putting some arbitrary ones. Here we'll put psi star, so sine x minus 2i times x, and then times the other thing. Oh, the one I'm trying to write here. Sine x plus 2i dx. And this looks kind of lengthy, and I will admit is a little tricky of an integral to solve. If you know any integrals, you will know that this is a little challenging. But this formula will give us the most likely value of x. Anyway, this whole thing with these complex conjugates will come up later when we go over things like spin and quantum computers, which is why I'm going through all of it now, because, you know, if you pay attention to some of this stuff, then later, when I go over things like vectors, this will all feel very familiar. But anyway, this is all how you calculate probability, you know. If you want to calculate probability at home, you just have to use this. And anyway, next time I will go more over imaginary numbers and why we care about them, you know. Why imaginary? And it should be very interesting because, you know, if you don't know much about imaginary numbers, it might be the first time you've ever heard of a use for imaginary numbers and why they're here in quantum mechanics. Anyway, see you next time.